We're going to have Jacob telling us about merging inductive relations.
I'm going to talk about merging inductive relations, and this is joint work with my advisor, Leo. So suppose that you're working in your favorite proof assistant with your favorite data type. For example, here I have an inductive definition of trees in Coq. I've got a leaf constructor depicted by the dots in the picture on the right, and a node constructor where each node has a natural number label and two children because they're binary trees. Well, often when we're writing programs that operate on data, the programs are going to expect their input data to be constrained in some way. So for example, if we have a program operating on binary search trees, our program might expect the input trees to be ordered. In Coq, we can use an inductive relation to represent constraints on our data. Here I have this inductive BST relation parameterized by a tree and two numbers, and what it means is that all of the labels on the tree should be in between those two bounds and in order. So the BST leaf constructor says that a leaf is considered to be ordered between any bounds low and high. And then the BST node constructor says that a node with a label X is ordered if the left child is ordered with labels less than X and the right child has labels greater than X. So for example, the 9 node at the top, the nodes to the left have labels less than 9, and the nodes to the right have labels greater than 9. So suppose that we have some sort of function operating on these trees. For example, this function insert, which takes a number in a tree and inserts it into the tree. And then suppose that we have some kind of property that we want to prove about that program. For example, here I have this theorem, insert preserves BST, which says that if a tree is ordered, then it will still be ordered after inserting a new node into it. Well, I could write a formal proof of this theorem, and that might be a good strategy, but that's a lot of work. So another thing that I could do is property-based testing. And in Coq, I can do that with this library called QuickChick. So what exactly can QuickChick do for us here? Well, we can take our inductive definition of BST, we can plug it into this QuickChick library, which is this existing work, and out the other end, it will generate a bunch of random ordered trees for us that we can use as inputs to test out our program on binary search trees. Now, another property that we might want our binary search trees to have is the balance property. Balance means that the distance between the root of the tree and every leaf is at most off by 1. So here the bal relation is now parameterized by a tree and a single number, which is the depth of the tree. The first two constructors there say that a leaf is considered to be balanced at either depth 0 or 1. And then the bal node constructor says that a node is considered to be balanced at depth n plus 1 if the children are balanced at depth n. So again, we could test out a program that expects its input trees to be balanced by taking our inductive definition, bal, plug it into this existing QuickChick library, and it would generate a bunch of random balanced trees for us. But what if we want to work with something like AVL trees, where our programs expect their input trees to be both balanced and ordered? How could we go about generating trees that are both balanced and ordered? Well, one thing that we could try using the existing work is we could first generate balanced trees, and then we could just filter out the ones that don't happen to be ordered. But it's pretty unlikely that n random numbers are going to be ordered. In fact, there's only a 1 over n factorial chance. We could also go the other way and try to just generate trees that are ordered. So we have that working, and then filter out the ones that aren't balanced. But again, that's going to be pretty unlikely. I couldn't tell you the exact chance, but it's pretty unlikely. But on the other hand, suppose that we had a single relation describing both properties at once. So there's no need to read the grayed out part yet. But an AVL tree is a tree that's both balanced and ordered. And here I have this AVL relation parameterized by now a tree and 3 numbers, where those first 2 numbers are the bounds from the BST relation, and the third one is the depth from the bal relation. And if I had this single relation describing both properties at once, then I could in fact plug this into QuickChick and generate trees which are both balanced and ordered. So inductive relations give a convenient way to encode properties of your data, but a problem that they have is that they're not very easily composable. Right? It's a lot of work to have to take every combination of properties and write a new inductive relation. So to solve that, for our research, we made an algorithm which will automatically merge inductive relations. So I'll show later how it can take BST and bal and produce the AVL relation from that. So what does our algorithm do in general? Well, in general, it will take as input two relations P and Q, which will both be parameterized by an element of a single shared type T, as well as many other unshared indices, these A's and B's, as you want. And then our algorithm will output a single relation PQ, parameterized again by a single element of this shared type T, as well as all of those separate A's and B's, such that PQ should be equivalent to the conjunction of P and Q. Well, in a sense, there's a trivial solution here, which is just PQ equals P and Q. But that wouldn't actually help us for generation, because we would still just have to find values satisfying both P and Q. So really what we want is to find PQ such that, if possible, it should never have a single variable constrained by two different properties anywhere in the definition. So we'll see how that works later. So let's take a look at how our algorithm works back with our specific example of BST and BAL. So we have these two input relations, both parameterized by a tree as well as some separate NAT indices. And our algorithm is going to output a single relation AVL parameterized by all three numbers in the single tree, such that AVL is equivalent to the conjunction of BST and BAL. So suppose that we have some tree T for which BST and BAL hold of some indices. Well, our algorithm is going to need to come up with some constructor that makes AVL hold for these indices, given as input some pair of constructors that we know BST and BAL must have that makes them hold for this tree T. So it might be kind of hard to see, but this is our BST and BAL relations again. So is it possible that if we have some tree T for which BST and BAL hold, that this pair of constructors, BST leaf and BAL node, could make them hold for that same tree T? Well, no, it's not possible, because leaf is not equal to node, so they can't create elements parameterized by the same tree. On the other hand, what about these two constructors, BST leaf and BAL leaf 0? Yes, they could, because they both make elements of their respective relations parameterized by leaf. So the idea is that our algorithm can start by looking at pairs of constructors from the two input relations. And for example, here we have BST node and BAL node. And the first thing that the algorithm needs to do is take a look at those output indices on the shared parameter and unify them to see if it's possible for them to be equal. Right? So unification takes two expressions and asks the question, is there some substitution of variables that makes these two expressions equal? Here there is. We can substitute M for X, T1 for L, and T2 for R. So these two constructors can create elements parameterized by the same tree. And then next our algorithm will substitute those variables so that the constructors are now written with exactly the same output value there. So then what our algorithm needs to do is create a constructor AVL node which has elements exactly when those two input constructors had elements. So the first thing that it does is it takes all of those output indices from the input relations and it puts them onto the output relation. And then we want this constructor to hold exactly when those two input constructors hold, so we can copy all of the inputs from BST node, and we can also copy all of the inputs from BAL node. And now we have this constructor AVL node, which holds exactly when BST node and BAL node hold. But is this actually useful for generation? Well, not really. I mean, if you focus right here, we have a variable L constrained by references to BST and BAL. So we're back to the original problem of if we want to generate an element with this constructor, we have to just generate an element L constrained by both BST and BAL. But luckily, if we recall our property that AVL is supposed to be equivalent to the conjunction of BST and BAL, what our algorithm can do finally is take these two references and combine them into a single reference to AVL. We can also do that to this pair of references here. And in the end, we end up with a constructor which is entirely recursive in the AVL type itself and makes no references back to the original BST and BAL types. So here's what it looks like if we apply that algorithm to all of the pairs of constructors in the original BST and BAL relations. We now have a merge type AVL. And so is this actually useful for generation? Well, here's a graph. On the y-axis is the rate at which we're generating trees. On the x-axis is the size of the trees. And the red line at the top there is generating trees using the merge relation AVL that our algorithm just came up with. And then the green and blue lines on the left are using the naive approach of generating with one relation and then filtering out from the other. And you can see we're able to generate much larger trees much more quickly. So let's take a look at this AVL relation that our algorithm came up with again. And in particular, look at these two arguments right here. So in order to make an element using this AVL node constructor, we're going to have to come up with some number x that's both greater than low and less than high. Now, of course, generating natural numbers in a range is a solved problem, but we can use this as an opportunity to put our algorithm to the test again. So now we have this inductive less than or equal to relation, and the goal for our algorithm is going to be to find a single relation between, such that between A, B, C holds if A is less than B and B is less than C. So what happens if we just take this and plug it back into our original algorithm from before? Well, it turns out that we get this. So is this any good? Well, this time there's a bunch of references back to our less than or equal to relation that the algorithm isn't able to eliminate. And that in itself isn't necessarily a problem, but really the problem is here in this constructor, where we have a variable m that's constrained by two different references to the less than relation. So this is not going to be helpful for generation. So to solve this case, as well as other cases, we added another step to our algorithm. So let's take a look at how that works. So here's our less than or equal to relation again. And in particular, look at this constructor less successor, which says that if n is less than m, then n is less than the successor of m. And notice that this constructor doesn't change the left argument n from the input to the output at all. So what does that mean? Well, if we remember this property that between A, B, C means A is less than B and B is less than C, then if, for any numbers, if B is less than C implies B is less than C prime, then just logically rewriting with that if and only if, that means that if B is between A and C, then B is between A and C prime. So this statement is logically true, and using it, we can just directly write a new constructor that will go into our output between relation of this type. So how does this all work together? Well, our algorithm will take two copies of the less than or equal to relation, which are up there but maybe invisible in gray, and it will generate this between relation. So the first thing that it does is it notices that this less successor constructor from one of the copies of our less than relation has this property where it doesn't change the shared parameter from the input to the output, and it directly lifts it with this step that I just showed. And then it takes the remaining pairs of constructors and it merges them together with the unification algorithm that I showed before, and we end up with this final answer for the between relation, which is successful because it never has a single variable constrained by two different properties. So our merging algorithm works in this case. Of course, it's not going to work in every case because generating data constrained by arbitrary properties is an undecidable problem. But it does work in a variety of other cases that we showed in the paper. So to give a couple of examples, on the left here, we were able to generate red-black trees. We had actually 3 inductive properties that described what a red-black tree was, and we merged all 3 of them together, and we were able to generate red-black trees. And then on the right, we were able to generate terms which are both typed and linear. We had a STLC typing relation and a relation describing linear terms, and we could merge them together and generate typed and linear terms. So also in our implementation, we automatically generate soundness and completeness proofs, which basically just mean that the merged relation is in fact equivalent to the relations that you started with. And the tactics that let you automatically generate these proofs, as well as the merging algorithm itself, are available in QuickChick 2.0. So you can run this command and try it out for yourself. Thank you.
Any audience questions? I see a few, yeah. Please come on up.
Hi, my name is Chen Zhuang from Purdue University. So my question is, I realized that in your examples, the conclusion of each inductive case is like P of some constructor and then a bunch of variables, right? So I'm thinking, can you handle something like P of a function on some variables? Like if you have
that's a good question.
Yeah.
So one of the steps that we do is unification of the two expressions. So yeah, no, the class of relations that are handled by this algorithm require the shared index to be basically made out of variables and constructors. Although you can get around that a little bit by making another argument and saying like x equals f of y and then put x in the output index.
Yeah, thank you.
Hello. My name is Jojo from Purdue University. It's a really nice talk. When I follow your talk, I have a question. So maybe it is you automatically goes, you have properties, a balance, a property is a BST, and you want to find the generator satisfies this property at the same time. So it's your method a little indirectly in my mind. why not? Because you actually winds up, so this is a property. You can simply conjunct them together, but you actually inductively merge them together. Why you not do the trick on the actual implementation of your test generator is actually say, you have a test generator, you merge the implementation of the two test generators together. Also, maybe there's a very easy solution that you have a test generator and each recursive call, if that is a BSD generator, you say, when you call the BSD generator recursive call itself, if that is not satisfy your balance property, you just filter it out. So it's not in your example, you run this generator, finally, you filtered out this low likelihood to get a balanced tree, but in each iteration, you filter out. Maybe I guess there's so many different solutions. The question is that why you don't work on the program, the test generator directly? Why you work on this property?
So the question is, why not merge the generators together?
Yeah.
I mean, it's an interesting idea. I hadn't thought about it. There's certainly going to be other ways to solve this problem, but I suppose there is at least some advantage to using the inductive relations, because when you're generating data that satisfies properties, this is an undecidable problem. So it's useful to be able to have a kind of intermediate representation that's easy to read and write, that you can sort of plug it into the algorithm and see what you get, and then maybe if you didn't get something useful, you could try something else. But yeah, it's an interesting idea.
Okay, thank you.
Hello, Ben Greenman from University of Utah. I'm wondering if you've thought about merging things beyond inductives, going more towards programs. So I'm thinking in particular of contracts. I like to write contracts for the things that I provide from a module, and sometimes it's nice to have multiple simple contracts that I combine together with a conjunction. And it seems like merging those would help the contracts run more quickly. So what could we do to go beyond inductives?
I'm not quite sure what form a contract takes. I mean,
Yeah, in general, contracts are just code. So
right,
I'm leaving it up to you to say what's in between.
The inductive relations that the algorithm works on have a pretty restricted form. It's basically like you have some data type, and then each constructor, has, like each reference to the inductive relation, you can give it expressions with constructors and variables. So I'm not quite sure how expanding that to a much larger class of things would work. But it's an interesting idea to look into.
Okay, thank you.
Okay, Yang Li from Portland State. So this question is mostly to pick your mind. You are thinking about merging inductive relations, but I wonder if you have thought about subtracting inductive relations. So maybe, for example, sometimes you define the AVL inductive relation and you define binary search tree. Now you want to get a balance by subtracting them. I wonder if that's something maybe some of variation of your algorithm can handle or something. Do you have any thought on that?
That's an interesting question. I hadn't thought about that before. That I could definitely see working with similar techniques. Right, I guess instead of the situation where you want to have some tree where there's a constructor from BSD and a constructor from BAL, there's a constructor from AVL, but not a constructor from BSD that makes it hold. So that would be interesting to think about.
Right. Thank you.
So maybe I can ask one last question while Thomas heads up there to plug in. This general problem reminds me of another one where we're trying to combine inductive definitions, and that would be where I have the original data type, and then I have a property of it. I want to turn that into an dependent version of the original inductive data type. Have you thought about any connections to techniques for that problem?
So you mean like you have list, and then you have length, and then you want to turn it into vector?
Yeah.
I see what you mean. Like, we do sort of expect this algorithm to work usefully in cases where the inductive type has some kind of similar structure to the tree, but I'm not quite sure. I don't know.
Okay. Thank you. Let's thank the speaker again.